This is Lab 4, the Circuit Construction Lab. My name is David Luton. This is Physics 2212, Group X11, Fall 2020. We'll be exploring several novel principles in this lab, the overarching one being that of the circuit. We'll also look at circuit components like resistors and capacitors. We'll explore Ohm's law, which relates voltage, current, and resistance. And finally, we'll look at the loop rule, which states that for any round trip, the potential difference sums to zero. We have two goals in this lab. First, to measure the potential around a series resistor circuit, which we'll look at first, and then to experimentally determine the time constant, RC, of a given circuit. As a preview, we found an RC of 6.0035 seconds for our experimental setup. All experimentation was conducted in a Java-based PhET simulation with a toolbar as shown at right. As for materials, all qualities, like EMF, resistance, and capacitance, were adjusted in simulation with an adjustment bar. We start with our first case, that of the loop potential. Now, for our given circuit, we're able to make a few predictions based on our starting parameters. We have an EMF of 3 volts, made up of two 1.5 volt batteries, and we have two resistors in series, one that's 47 ohms and another that's 100 ohms. Since these are in series, we can sum resistances, finding the total resistance of 147 ohms. We have our resistance, and we have our voltage in the form of EMF. Using Ohm's law, we can solve for current. This was found to be 0.0204 amps, whereas in the simulation this was found to be 0.02 amps, probably as a result of rounding. We also measured potential difference between given points, as shown in the middle diagram. As expected, the loop rule was proven. That is, the potential differences summed in a round trip summed to 0 volts. Adding a parallel ammeter above the 100 ohm resistor gives the current a path of least resistance, bumping the resistance up to 0.06 amps, circumventing the 100 ohm resistor. We now move on to our second case, the resistor-capacitor circuit. A few important points about this experiment. To start, the capacitor was charged to 9 volts with a battery. The battery was removed, and the circuit reconnected, discharging the capacitor through a resistor. In this case, a light bulb. Now, as the capacitor discharged, change in voltage of the capacitor was measured at 2-second intervals over 20 seconds, amassing to 10 data points. This was logarithmically graphed, as shown in the graph at top right. A few key values to note. The resistance of the bulb was set to 30 ohms, and the capacitance of the capacitor was set to 0.2 farads. Thus, our time constant, RC, is just the product of these two values, 6 seconds. In our experiment, our slope is the negative inverse of the time constant. This was found to be 6.0035 seconds. Again, for our purposes, these values are the same. Now, let's put these results in context. If we'd used an actual ammeter in an electrically equivalent circuit, the amount of current flowing through that ammeter would be slightly lower than what the simulation predicts. This is because all circuit components, wires included, have some innate resistance. So the current flowing through that ammeter, if only a small amount, is siphoned away. In a similar vein, if our resistor-capacitor circuit didn't have a resistor, our capacitor would charge instantaneously, since there's no cap to the amount of current flowing through our circuit. In real life, however, since wires are slightly resistive, a theoretical limit to the amount of current flowing through the wires exists. This concludes Lab 4, the Circuit Construction Lab. Thank you for watching.